Hello everyone and welcome back to your YouTube channel. And welcome to this very interesting video today. And the video is dedicated to the calculation of kinetic energy, acceleration, and other electromechanical variables in a synchronous generator. For that reason, let me start with this very simple exercise. Consider a 60 Hz 4-pole synchronous generator. It has a rate apparent power of 85 MVA, rate stator voltage of 13.2 kV, this is line-to-line RMS voltage, and it has an inertia constant, rotational inertia constant of H equal 6.42 megajoule per MVA. Now, this machine is subject to constant acceleration. The acceleration alpha is equal to 48.68 RPM per second, or equal to 584.23 electrical degree per square second. This acceleration is constant for 15 cycles of the rate frequency. Now we have here two very interesting questions. The first question is calculate the change in the angle delta in electrical degrees in that period. Second, calculate the rotational speed in revolution per minute, RPM, at the end of 15 cycles. In this case, we are assuming that the synchronous generator is synchronized and is connected to a very large power system. And also, this machine has not accelerating torque before the acceleration period begins. Well, now what we need to do, something simple. We define the input data. Here we are including the acceleration, 584 electrical degree per square second. Also, we are defining the angular acceleration in 48.68 RPM per second, rate frequency 60 Hz, acceleration time 15 cycles, and the number of poles is 4. Now, the first task here is to calculate the acceleration time, but in units seconds. Again, the first step is calculating the accelerating time using seconds. To do so is very simple, because there is something called the time period, and for a signal with a frequency f in hertz, the time period is basically 1 divided by the frequency in hertz. For that reason, to calculate the accelerating time in seconds, what we need to do is calculate the product between the acceleration time in cycles and the period in seconds. We do that here. We calculate the period, dividing y1 by the frequency, and then we multiply 15 cycles by the period of one cycle, and we obtain here something quite interesting. The acceleration time for 15 cycles at 60 Hz is equal to 0.25 seconds, or in other words, 250 milliseconds. And the acceleration here is 584.23 electrical degrees per square second. I am presenting here the acceleration in other units, 10.19 radians per square second, also 292.11 mechanical degree per square second, and finally this is the data, 48.68 RPM per second. To calculate the change in the rotational angle delta, we can use this equation over here. We need to understand that delta delta, this is delta delta. where the first delta is the capital Greek letter delta that represent changes, and the second letter is the lowercase delta that represent the angle. For that reason, to calculate the change in the rotor angle in electrical degrees, what we need to do is use this very simple equation, half of the acceleration multiplied by the square of the time. In this case, the acceleration should be defined in electrical degree per square second, and the acceleration in seconds. When we put the number together, very simple, it's just a mathematic product over there. The change in the rotor angle delta delta is equivalent or equal to 18.25 electrical degree. Now the next step is calculating the mechanical synchronous speed. Very simple, all my students, they can obtain this equation, 120 frequency divided by poles, and from there the mechanical synchronous speed in RPM is 1800. For that reason, to calculate the final speed is very simple. We know the initial speed before the acceleration period, and the initial mechanical speed is 1800 RPM. Then we multiply by the acceleration in RPM per seconds, and we multiply that acceleration by the duration of this acceleration process. In other words, what we need to do is basically 1800 RPM plus the acceleration times 0.25 seconds multiplied by 48.68 RPM per seconds. And at the end, we obtain the final speed, rotational speed in this machine after the conclusion of the acceleration process, 15 cycles, and that final mechanical synchronous speed is equal to 1012.17 RPM. And this is the answer for the question number 2. And we reach the very end of this exercise. This is the end of this solution, and I hope you enjoyed the video, and if yes, please subscribe to the YouTube channel and also leave a comment or message. If you have any question, please drop the comment or email me. Well, this is all for this video today, and I will see you at the next one. Thank you and bye now.